All right, good evening, ladies and gentlemen. Thank you very much for tuning in. This is the night before the exam physics paper 2 revision hangout. Thank you to anyone that's tuning in live now. If you are watching live, feel free to put a message or just say hello on the frog wall. Make me feel like I'm not just talking to a computer. So say hello if you can. You don't have to, your messages won't be seen by other people on the frog wall, just me, and you feel free to ask questions as well. Okay, so a couple of reminders before we get going. I know you'll be in good practice for this, but get a good night's sleep tonight. Eat plenty of food. Come in and get a good breakfast with us if you want to. And this last one, double check your equipment today, because for this physics paper, this is the paper that you need your protractor for. Okay, and we're absolutely sure you're going to need your protractor for this exam. Obviously, a couple of people have asked, what do we need protractors for? They're for measuring angles. Okay, so there's a couple of possibilities of when you might need to use a protractor, possibly for measuring angles, and it may also be for maybe when we do refraction, measuring your angle from the normal. Okay, so bring in your protractors tomorrow. We're almost certain that you're going to need it. Okay, let's make a start then. So I'm going to start with the required practicals, okay? There's 5 required practicals if you're a separate scientist, 4 if you're a combined scientist. So we're going to start with the springs required practical. They love asking questions about these. So what's the required practical about then? Well, this is a practical that relates force and extension. Okay, and now this is basically adding masses onto a spring and looking at it get longer. And it's using the equation of F equals K times E, force equals spring constant times extension. So what is the practical about? Well, adding masses to a spring makes the spring get longer by the same amount each time until too much weight is added, and then the spring goes past its elastic limit and it won't return to its original length. So this is a practical involving looking at adding weight and looking at the extension. Now the experiment uses the equation of F equals K times E, where force is the weight applied to the spring, and the spring constant K, and the extension E. Now they love asking questions about this, about what is the extension exactly. Well, the extension is the length, the full length of the spring once it's had masses added onto it, take away the original length. So your extension is the difference between the two. It's that little bit there. Okay, now if you ever see a graph for Hooke's law where the graph doesn't go through 0, 0, for example, that shape there, if the line doesn't start down here, what they've done is they haven't calculated the extension, they're just using the full length of the spring. So keep an eye out for that, because of course the spring has already got a length on it, it's already got a length before you put any masses on it. Okay, so let's have a quick look at a method then. So here's our practical equipment. We've got a retort stand here, a spring there, we've got a meter ruler down here, and in a second I'll talk about the graph down there. So your method would be that you're going to attach a ruler to a clamp stand, and you're going to put a pointer or an arrow to read the length easily. So you might attach a little arrow or a pointer at the bottom of the spring, just so that you can read it off of the ruler easily. Measure your starting length, add 100-gram mass, for example. Now, if you're adding a mass in grams, you might need to talk about turning that into weight. So to turn it into weight, you're going to use weight equals mass times gravity. And they would probably tell you in the question that gravity is equal to 10 or maybe 9.8, depending on how accurate they want to be. And you would use weight equals mass times gravity to find the force of that 100 grams there. So 100 grams you turn into kilos, 0.1 kilos, times that by a strength of gravity of 10, and you'd find that 0.1 kilos is 1 Newton. Just to turn that into weight. Okay, you're going to record the final length of the spring each time you add another mass. You're going to do the final length minus the original length, and that gives us the extension. And we would plot a graph of, as you can see over here, you'd plot a graph of extension versus force there. Okay, finally, the spring should extend by the same amount each time. If it extends more, it has passed its elastic limit. So this little part of the graph up here, where it's no longer straight, so I'd say probably from around there, this part of the graph up here doesn't follow what we call Hooke's law, because it's not directly proportional. So because it's not directly proportional, that's where the spring's been overstretched. Someone's put too many masses on it, and it will never go back to its original length. So we say it's past its elastic limit. Now, this part of the graph here, where it's straight, we can say that force is directly proportional to extension. But in this case here, in this graph here, in this example I've chosen, they've done that deliberate mistake of they've included the original length of the spring. So they haven't done the extension. And how we can see that there is, well, when there's no force on the spring can't have any extension because there's no force on it. So it should be starting down here. But what they've done is obviously the length of the spring originally was 50. So that's why when there's zero force on it, it starts at 50. Okay, so there is a required practical on acceleration. And this required practical is to do with using the equation of F equals ma. This apparatus, all of this apparatus over here, is used to prove that F equals ma. So that is force equals mass times acceleration. Now the equipment, really roughly in this diagram you can see here, is that there is a glider or something that can slide across a track, and we've got some weights over here which are there to pull the glider across the track. Okay, so a trolley can glide on a frictionless track. The reason why it's frictionless is because we want to apply a force to an object. We don't want any forces in the opposite direction. We don't want any resistance forces acting on it, just the force that we're applying to it. So weights down over here, we can apply weights at one end of a string, and that's going to pull the trolley or the glider across the table. And it's going to pull it with a constant force because gravity is the force acting on the weights, and it's just going to pull it straight down. Light gates can be used to calculate the acceleration. Remembering we're doing force equals mass times acceleration. Well, we need to know each of the things in the equation here, so we can use light gates, and I'll explain a little bit more about those in a minute. Now, for this practical, we're either going to be changing the force that it is being pulled with, or we're going to be changing the mass of the trolley. Just like any science experiment, you only want to change one thing at a time, and we're going to see the effect of changing the force or changing the mass of the trolley to see the effect on acceleration. Acceleration is what we would be measuring in this experiment. Okay, so the method for this practical then. So we're going to attach the trolley to a string, pass that string over the end of a pulley at the end of a track. You're going to add masses to the end of that string there, and this will provide a constant force on the trolley. Now you're going to use light gates to measure the acceleration of the trolley. You're either going to increase the mass that's placed on the trolley, so we're going to make this part heavier up here by stacking masses on top of it to make it heavier, or you're going to be putting masses on top of the weight down here to pull it faster. Of course, the more mass you put down here, the bigger the force you're accelerating your trolley with. So what are the results going to be from this practical? Well, because force is directly proportional to acceleration, doubling one is going to double the other. If I double the force I'm pushing something with, I'm going to double its acceleration, because we can see there that F equals to m times a. If m stays the same, if I double F, I'm going to double the acceleration. Now with mass, if I increase mass, that does the opposite. Me increasing how heavy something is will reduce the acceleration. So we can say it's inversely proportional to acceleration. If I double the mass, it's going to halve the acceleration. So if I double how heavy the trolley is, because the force I'm accelerating with should stay the same in an experiment, I'm going to halve the acceleration. So they're inversely proportional. Okay, now how the light gates work, if we have a quick look at this example here, we're going to have a piece of card on top of our trolley, and the card is going to pass through the two lights. Now, I can't guarantee that this will come up in the exam, but if it does, then this will give you a really good indication of how to answer these types of questions. So how the light gates work. The light gates work by measuring a time interval that they're interrupted for. They're connected to a computer, and that computer will record when something goes through the beam, when something blocks the beam, it records how long that time interval's for. And there's the piece of card on top of the trolley that's going to break that beam. So they're attached to a computer that can use the length of the card to work out the speed that the card is going through the light for. So that's just simply speed equals distance divided by time. Speed equals the length of the card divided by the time interval it breaks the light for. So speed equals distance over time. Okay, the card is U-shaped, meaning it breaks the light twice. The computer works out the speed of the first card and the speed of the second card. And if you know the speed of two different things, the speed at the front of the truck is going, the speed when the back of the truck goes past, you can work out the acceleration using change in speed divided by time. Okay, so measuring waves then, there could be a required practical on different ways of measuring waves, whether they be on a string. For example, here we've got a vibration generator generating waves on a string, and you can see the string is going to be moving up and down. It could be waves on a spring, so that could be, the spring could be sideways, the spring could be vertical as well. And looking at the areas of compression, where the bits of the wave are squished up, and rare refraction, where the bits of the wave are spread out. We might be doing a required practical on waves in water, so we're going to look at a ripple tank, or maybe waves in air as well, measuring the speed of waves in air. Now, just a couple of tips about these. A vibration generator for lots of these is used. A vibration generator generates the vibrations you want at the frequency you want. So you can decide how quickly these things go backwards and forwards, and that's going to tell you the frequency of those waves. Now, if the waves are really small in any of these practicals, measure lots of them. Measure the length of lots of them and divide by the number you've measured to get the length of one of them. That's going to make your results a little bit more accurate. Okay, so let's have a look at the first one, ripples on water, and we're using this equation up here of V equals F times lambda. So this is wave speed, velocity, equals the frequency of the wave times by the wavelength of the wave, how long one wave is. Okay, so let's have a look at our equipment over here then. We've got a light bulb above this table. The table's filled with a little bit of water. We've got an oscillating paddle, or a dipper, and that dipper is just going to dip up and down, and that's attached to a power supply there. And the power supply will be your vibration generator, and that'll tell you exactly the frequency of the number of times this dips up and down. Now, because this is dipping up and down into a pool of water, and we've got a light above it, you're going to see shadows appear underneath. Where the water is thicker, you're going to get a dark line, and where the water is thinner, you're going to get a light coloured line. Okay, so we can see the wave patterns on the viewing screen, or you can see it on the table itself. So what would the method for a practical here be? Okay, so we're going to fill a couple of centimetres of water in a ripple tank. Really doesn't matter how much water, just a small amount of water. You're going to connect a dipper to a frequency generator, and you're going to set it to the frequency you want. And this is going to tell you F. And just remember here that with any practicals, we're looking at finding out the things that go into the equation. So V equals F lambda is such an important equation for this practical. So turn on the lamp above the water, dim the lights in the room so you can see the shadows easily. Measure the length of 10 of the moving wave shadows that appear under the tank. Now one is going to be too small to measure easily, and this is important. If you're measuring the length of 10 waves, it's 11 lines, okay, because you've got a line at the start and the end, so you're going to have 11 lines to measure 10 waves. So that's going to tell us the wavelength. You measure 10 of them, divide by 10, it's going to tell you the wavelength. Now, finally, if you know your wavelength, you know your frequency, you can use your wave speed equals frequency times wavelength. Now, the only difference you may see in the exam is that they might possibly use a strobe light. A strobe light is one that flashes at the same rate as the dipper. And if it flashes at the same rate as the dipper, you're going to see the waves are going to appear to stand still underneath. Okay, and that's really nice because it makes it easier to measure the length of 10 waves. If they're all stood still, you can measure the length of 10 more easily than if the light is on permanently. You're going to see the waves move across the screen, and it'll make it more difficult to measure the length of 10. Okay, so waves on a string then. So here we've got a vibration generator. Now we've got our piece of string there, and you can see that there's the piece of string is in two positions here, in the up and the down position. Well, it's important for you to know that one wavelength is made up of two half wavelengths. And that might sound really obvious, but one wavelength has to include an up part and a down part. Okay, so when it's moving really quickly, they kind of form a shape that looks like that, but of course the string is only ever in one position. We've got to measure one full wavelength, which includes an up and a down part. Okay, so what's the method for this then? Well, we're going to attach one end of the string to a vibration generator, set it at the frequency you want. This is going to tell you F, and again our equation is V equals to F times lambda. Attach one end to a string, to a vibration generator. It's going to tell you the frequency you want. You're going to put some weights on the other end and hold it over a pulley. Now, why you do this is just to make it tight, so that we don't have a loose piece of string, because a loose piece of string won't show the waves. So make it nice and tight. Measure the length for a wavelength. Again, two half wavelengths. You might want to measure a few and divide by how many to make it accurate. and this tells you the wavelength. So you might find you've got loads of waves appearing on this piece of string. Measure 10 half wavelengths, that'll be 5 whole wavelengths, and divide your number there by 5. Okay, so this is that'll tell you the wavelength. You get the frequency from the vibration generator. Again, use V equals F times lambda. Okay, so in this example, we have got a vibration generator again. Sorry, this is a frequency generator, a signal generator connected to a speaker, and we've got two microphones here. There's one behind the other, so you can only see one of them at the moment, and it's connected to an oscilloscope. An oscilloscope is something that lets you see a wave on a screen. Now, if you attach a speaker to a signal generator, and this will generate a single note at a frequency you want. So this will tell you F from the equation V equals F lambda. An invisible sound wave will appear in front of the speaker with peaks and troughs in it. So let's have a look at this invisible sound wave here. Now, of course, sound waves really are longitudinal, but we turn that into a transverse wave just so we can see a picture of it. But really, of course, sound waves are longitudinal waves. If my two microphones are in the same position, one behind the other there, they're both going to see exactly the same wave appear on the screen. So this is the speaker, microphone 1, microphone 2. They're both the same distance from the speaker, so you can see there the same wave is being picked up on both of them. Now, we're going to slowly move one of the microphones away from the speaker until it is a complete wavelength away from the other. So let's have a look and see what we mean there. We're going to move the other one away until you get the same picture, but the wavelength has been moved one across. So you would see this wavelength move and slide across the screen until it is one away. Now then, when you know you've moved your microphone one away from one full wavelength from the other microphone, you're going to be able to get a ruler up, and that ruler, the distance between the two microphones, will tell you the length of one wave. Clever. So this tells you the wavelength. The frequency will come from the signal generator, and then again use V equals F times lambda. You can see how important that equation is for so many practicals. Okay, so now measuring sound waves in air, a slightly different method for this one. This time we're going to be using speed equals distance over time. So we've got over here, we've got two microphones connected to a laptop. We've got a set distance that we choose between the two microphones. And then the microphones are going to be connected to a computer that will measure the time delay, the delay of the time going between the two microphones. So you might want a really short, sharp noise for this, so a bell or a starter gun to make a short noise. The laptop records the time delay for the wave to pass between the two microphones. And this will tell you the time t that the sound took to go past. You'll need to measure the distance with a ruler between the two microphones, and finally use speed of the wave equals distance divided by time. Okay, another example, another way of measuring the speed of sound is slightly less technical, and this is the echo method. So in order to do this, you're going to need something to make a loud noise, a cannon, for example. You're going to want a flat wall and a long tape measure to know the distance you are away from the wall, and a timer as well to be able to time how long it takes for the sound to come back. So measure a distance from the wall. This is going to tell you the distance you are from it. Make a loud noise. Use the stopwatch to record the time for the sound to travel to the wall and back. Once you've got the time for the sound to travel to the wall and back, divide that by 2, because it went there and back again. Then use speed equals distance divided by time to find the speed of sound in air. Not as accurate as the previous method, but of course you could repeat this a lot of times. Increase the distance you are away from the wall would also increase the accuracy of your experiment. Okay, next required practical, radiation then from different coloured surfaces. So if we're going to investigate how the surface colour affects the amount of infrared radiation emitted. So here's a picture of a Leslie cube. Here it is with an infrared image. And you can see here in this infrared image, you can see that there's definitely a difference in the heat being given out. And I'd probably say that hotter is whiter. So that side there would probably be black, and that this side here would probably be maybe white. They're not the same picture, not the same Leslie cube as up there. Okay, so what would our method be for this? So fill a cube that has different coloured surfaces with boiling water. And you fill it with boiling water so that each surface has got the same temperature. You know that inside it's nearly 100 degrees. You're going to use a ruler to make a line, a set distance away from the cube. You're going to hold an infrared thermometer at that same distance from each side, not like this person is, a little bit too close there. Get it away at the line, then hold it the same distance away each time, because distance affects the amount of radiant temperature you can measure. So you're going to record the radiant temperature for each coloured side, and the expected results would be that matte black is the best emitter. That should give you out the highest temperature, and shiny silver should be the worst emitter, the lowest temperature that's recorded. Okay, now for separate scientists only, we've got a required practical here. This won't take long for everyone else that's listening, or you can pause and go get another biscuit. So the aim of this is to see how different materials bend and refract light differently. Now the IV, the independent variable in this, would be the type of the block. Dependent variable would be the angle of refraction, and a control variable could be the angle of incidence. And we're going to have to be changing the type of block and shining light in it the same way each time. So you can see here we've got a normal drawn at the surface. A normal is an imaginary line that we draw there, and we draw it simply so we can record our angles of incidence and angles of refraction there. Okay, so our method, we're going to draw around the block on a piece of paper. Put your glass block on a piece of paper, draw around it. Shine a beam of light at the block so it comes through the block and out the opposite side. We don't want it bouncing off of the corners and scattering all over the place. We want it to come through the block nice and clearly. We're going to mark the beam using X's. So you've got your ray of light, you're shining it at your block, just put some X's down where it goes in, put some X's down where it comes out. Obviously, the more X's you use, the more clear your line is going to be. Okay, we're going to remove the block, turn off the light, possible risk of burning if it's a light bulb. Join up the X's so they show a beam going into, through it, and out of the block, just like we've got here. Now, obviously, you're not going to have any X's on the middle. You've just got to join up where the lines go in and come out. You've got to then draw a normal using a protractor at 90 degrees to the surface where the ray hits the block. That's our imaginary line and goes into the block all the way there. We can then measure and record the angle of incidence, so that's between the normal and the ray, and we can then measure the angle of refraction between the normal and the ray that's inside the block. Okay, then that's our first set of results for the first block. We're then going to replace the block, keeping the angle of incidence the same each time, but measuring the angle of refraction each time. And what we'll find is that the more dense the block, the bigger the refraction that will take place. So the ray will be bent even more with a more dense material. Less dense materials, it would refract it less. So it would keep going almost straight in a straight line with less dense materials. Okay, so still on separate physics, reflection then, and keep listening if you're watching combined. Reflection through different surfaces then. So what's the aim of this practical? The aim is to see how different materials reflect light differently. And the independent variable there could be the type of the surface. Dependent variable could be the angle of refraction, the brightness of the reflection, because different materials might dim the light, and the width of the reflected beam as well. And we're going to look into that in just a second. Now, your control variable would be the angle of incidence. You're going to want to shine this light in at the surface the same each time. So the results we would probably be expecting here is that a smooth surface, like a mirror, is going to reflect a beam with exactly the same width, the same angles, and the same brightness. But a rough surface, like a piece of paper maybe, or a piece of metal that's still shiny, but maybe you can't see your image in, that might dim the brightness and it might spread the beam out. And that's because a flat mirror is going to give us specular reflection, whereas a bumpy surface might give us diffuse reflection. So the rays might still come off in roughly the same direction, but might spread out a little bit more. Okay, so our method for this, we're going to place a mirror upright on a line on a piece of paper. We're going to shine a beam of light at the mirror so you can see the reflected beam. You're going to mark the beam using X's, mark the width and the brightness of the beam. Brightness could just be done from judging by eye, which gives a brighter or dimmer beam. Marking the width, you could maybe draw lines on either side, draw lines down either side of the beam there. Remove the mirror, turn off the lights. Join up the X's so they show a beam going into and out of the mirror. Draw a normal, that's at 90 degrees to the surface, using a protractor where the ray hits the mirror. Measure and record the angle of incidence and the angle of refraction. Replace the mirror with other surfaces, keeping the angle of incidence the same, measuring the angle of refraction, measuring the brightness or the beam width each time, depending on what the practical is for, what you may have to measure. Okay, so those are all our required practicals then. Feel free to pause and go back to any of those if you're not sure. Now we're going to go through a few of the math skills that are needed for this physics paper 2. And we're going to start off with recalling paper 2 equations and their units, a really important part of the topic this. So first equation we come across is weight equals mass times gravitational field strength. W equals m times g. So this is the equation that tells us that mass is not the same as weight, and we're going to have a closer look at that shortly. So work done then, the work done to move something, the work done is found by the force that you're applying to move it times by the distance you move it. Okay, so this could be maybe someone dragging a box across the floor. What work do they do? Well, it's the force they're pulling it with times the distance they move it. Okay, our spring constant equation that we've already seen, force applied to a spring, that'll be the weight that's downwards, is equal to the spring constant times by the extension of that spring. Some people rearrange the last two letters to make this more memorable, and I'll let you do that inside your head. Moment of a force then, this is for separate scientists only. A moment is force times distance, and that's a perpendicular distance from the pivot. Okay, another separate science only equation here, pressure equals force divided by area. So you may need this for this paper, particularly when we come to fluid density. So an equation that everyone needs to know, distance travelled equals speed times time, or speed equals distance over time, an equation you've used for many years. So a few of the units then, so don't forget with units, you want to check for those banana skins as soon as you get to a calculation question. Do you need to convert your units into the SI units? So this is the list of SI units, and you're going to see there's only one you really need to know about that's a bit different. So I'm sure you can spot it. So both weight and force are both measured in newtons. Okay, so a weight and force are both vector quantities which have got directions. Now mass is the odd one out. Out of all of the SI units, mass is the only one that has kilo at the start of it, because a kilogram is the SI unit of mass. But normally, if you see kilo at the start of a unit, you need to convert that into the SI units. You need to get rid of the kilo by timesing by 1,000. Okay, so distance in meters. A moment for those separate scientists is Newton meters, n/m. Pressure is measured in pascals, and area is measured in meters squared. Okay, of course, speed is measured in meters per second. Okay, a few more equations to recall then. We've got acceleration, which is the change in speed over the time taken. So the change in velocity could well be your starting velocity, take away your final velocity, take away your start velocity. That will tell you your change, the change in speed. Okay, so final speed, take away start speed, as in the change in speed. Okay, our force equals mass times acceleration, and if I teach you in year 11, I'm not going to say what I normally call that because I'm not cool enough to use that word. But you can rearrange those last two letters there to change that into a more familiar word, a more streetwise word than I can use. Momentum equals mass times velocity. So the momentum an object has is its mass times velocity. Wave speed equation, really important equation, this one, V equals F lambda, or velocity wave speed equals frequency times wavelength. Okay, so velocity or wave speed equals frequency times wavelength. Now some units for these then, we've got acceleration. Acceleration is like speed, but it's how speed changes per second. So we say it's meters per second, or meters per second squared. Really important we remember that too up there. Okay, time is measured in seconds. We all know that. Force in newtons, mass in kilograms. Now momentum is one you can learn, or you just learn the equation, because of course m is in kilograms, v is measured in meters per second. So to work out the units for p, all you have to do is times those two things together. So we get kilogram meters per second. Okay, so that's our unit for momentum. Don't need to remember it as long as you know you can work it out from the equation there. Okay, wave speed again, meters per second. Now frequency is measured in hertz. Frequency measured in hertz means 1 wave per second. 1 hertz is 1 wave per second. and wavelength measured in meters. Okay, now you might be asked to select equations from the sheet, from the equation sheet you get given. Now, these are the three equations on the equation sheet which will appear on both combined and separate science. Now, you'll get some equations on there that only apply to the paper ones. Okay, obviously, if they're only applied to the paper ones, I haven't included them here. So there's this equation here, final velocity squared, take away initial velocity squared equals 2 times acceleration times distance. Now, what they would be likely to do here is they're going to tell you 3 out of the 4 things, and you're going to have to work out the other one. And I'm going to help you later on with rearranging this equation just to see how easy it is. Okay, now this one is to do with waves. Okay, so period of a wave is how long it takes for one wavelength to go past you. Okay, so it's a length of time. So period will be measured in seconds. Okay, measured in seconds. So for example, it could take 3 seconds to go past you. Now, frequency is a measure of the number of waves that go past in 1 second. So frequency is measured in hertz. Okay, now to convert between the length of time it takes for one wave to go past into how many waves go past in a second, all you have to do is do 1 over. Now, when you rearrange this, this will go into your equation triangle, exactly the same as all the rest. You'd put a 1 up at the top, you would put your periods down the bottom and your frequency down the bottom. Okay, and because you know your equation triangle has got divide by signs and times by signs already in there, you cover up the thing you're looking for to rearrange it. So period equals 1 over frequency, frequency equals 1 over period. Okay, so frequency equals 1 over period, and you would be able to rearrange that yourself in the exam, or just recall it. But don't be put off by the fact there's a 1 in there. That 1 still has to go at the top because it's 1 divided by frequency, so 1 divided by frequency. Okay, for the higher tier then, we've got this equation down here of F equals BIL. Now that's for higher tier only. When it comes to practicing those questions with lots of terms in, write these letters here next to the numbers that they're going to be giving you. Okay, and that will really help you to be able to pick out this equation. And particularly if you see anything, any question which mentions magnetic flux density, you know that there's only one equation relating to that. It's on the equation sheet. And look out for the bits on the equation in the questions where they say use equation sheet. Okay, they really do say that a lot in the questions. Keep an eye out for that. Circle it, because if they tell you to use that, it's on here, and that's going to be easy marks for you to write it out, substitute in your numbers. And I would say always, always, always show your working. Because the number of times in the mock exams where I mark those, people get the wrong answer, but can still get marks because they've done the first couple of steps right. And the first couple of steps that could be just putting the numbers in the right places in the equation. If you know B, you know I, you know L, put them into the right equation, write out your equation again with the numbers in the right place, you know, work it out on a calculator and write your answer down. There can be marks for just showing your working. Okay, so separate scientists only, here's a few equations that you might have to pick out from your equation sheet. We've got the pressure due to a column of liquid being the height of the liquid, the density of the liquid, and the gravity field strength pulling it down. That's going to tell you the pressure that's due to a column of liquid. Go and have a look at the separate science video if you want to go and find a bit more detail about that one. Then we've got our transformer equations. So these two equations here would be relating to a transformer. There's could be the iron core of a transformer, and we're going to have a coil of wire on one side and a coil of wire on the other side. And these numbers here would relate to, remembering that the ratio of the voltages across these two things is equal to the ratio of the number of turns of these coils here. So P just relating to primary side, that's the input side. The secondary, the S is relating to the secondary side, that's your output side. So we've got an input side primary, output side secondary, and the ratio of the number of turns is equal to the ratio of the voltages. Okay, then we've got an equation down here, which is basically saying, because we know, remember from paper 1, that P equals I times V in electricity, this equation is basically saying that the power into a transformer is the same as the power out. That's if they're really efficient. So this is just a way of working out. Let's say I knew the current going into a transformer, and I knew the power coming out. I would be able to work out the missing value there. Okay, now with lenses, magnification equals image height over object height. Lovely that they give you that. And then this last one, force equals change in momentum over time taken. Now, I spent a bit of time on the separate only video going through this, so feel free just to fast forward in that other video to this bit here. And again, feel free to post up any questions you have on the frog wall, or just say hello if you want to, as this is our last hangout for your year group. Okay, so let's have a little look at some practice questions here, and we're going to see what other skills, what other math skills might we need. Okay, so this is a typical exam question on this waves from the waves section. A TV station broadcasts at 500,000 kilohertz. The waves travel through the air at 300 million meters per second. Calculate the wavelength of the waves broadcast by this station. Show clearly how you work out your answer. Could be up to 4 marks for this question. Okay, so first off, don't forget to bug it, and that means box your command word, underline your key numbers or words, glance at the number of marks over here to tell you how much you're going to need to put in. Okay, so underline your command, your values in there, put a box around the command word. Okay, so first off, we need to check our units and we need to convert them if they're not in the right unit. So look for your banana skin straight away. Okay, we've got a banana skin, 500,000 kilohertz. Kilo, as we're going to see in a second, means times by 1,000. So really, 500 kilohertz is really 500 million hertz. Okay, recall the equation. V equals F times lambda. Wave speed equals frequency times wavelength. Rearrange that, and we could do that by putting it into an equation triangle. And I'll show us a bit more detail about how to do that shortly. And we're going to substitute in our values, so keep writing it out, but this time we're putting in our numbers. That slash there just means divide by, and that gives us an answer of 0.6. Okay, so we really do need to know these prefixes here. So we've got the ones in red here, kilo, mega, giga, are just getting bigger, and then we've got milli, micro, nano, are just getting smaller. Okay, so what do they mean? Okay, giga, for example, turn 11 gigahertz into hertz, because it's not in an SI unit. So we would times that by 1 billion, or times it by 1 times 10 to the 9. Okay, mega. Mega basically means million. Convert 3 meganewtons into newtons, maybe the gravitational attraction of a planet. So 3 times 1 million, or 3 times 1 times 10 to the 6. Or sorry, 3 times 10 to the 6. Okay, kilo means 1,000. So 3.2 kilometers, let me try that again. 3.2 kilometers into meters, 3.2 times 1,000, or 3.2 times 10 to the 3. Okay, no prefix is obviously what we want. We don't want, we want all of our SI units just on their own, apart from mass, which comes with a kilo on it. So kilograms is what we want mass to come as. So milli then, milli means divide by 1,000, turn 6.5 millinewtons into newtons, 6.5 divided by 1,000, or also written as 6.5 times 10 to the minus 3. Micro then as a prefix, convert 3.35 micrometers into meters. This time we're going to divide by a million, or 3.35 times 10 to the minus 6. Noting there that the minus is just us shifting the decimal place to the left, making the number smaller, as opposed to when it's a positive number there, we're shifting the decimal place to the right. Finally, nano, convert 6.5 nanoseconds into seconds, so we're going to divide by 1 billion. Now notice there that the powers go up by 3, so 10 to the 3, 10 to the 6, 10 to the 9, and they go down by 3s when we get smaller, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. Okay, so let's put some of this into practice then about using significant figures or decimal places. A mobile phone network uses microwaves to transmit signals through the air. The microwaves have a frequency of 1.8 times 10 to the 9 hertz, hertz meaning 1 wave per second, or waves per second, and they travel at a speed of 3 times 10 to the 8 meters per second. Calculate the wavelength of the microwaves, give your answer to 2 sig fig. You can see the units are already done there, and we've got our number of marks down there. So box, underline, glance at the number of marks, check your units for banana skins. Okay, units are fine, meters per second and hertz. Now then, recall the equation, rearrange it. So V equals F times lambda becomes lambda equals V divided by F, and I'll show you equation triangles in just a moment. Substitute in our numbers, so write it out again, but this time putting our numbers into the right place. So lambda equals our 3.0 times 10 to the 8 divided by our 1.8 times 10 to the 9, and the calculator should come out with a number like that. And then this is really important why we underline these parts of the question, because they're easy marks for turning it into the right number of sig fig. So we want two significant figures for this. So 2 sig fig really does refer to, we've got to write down two numbers. Okay, so I've only written down the two important numbers after the decimal place. But I look at the next number, and if it's above 5, it makes me roll that number up. So my 1.6 is going to become 1.7 because of the number after it is bigger than 5. If this number here was 0.163, it would stay as 0.16 because that number there is less than 5. Okay, so as an example then, how would we turn this if it was 1 sig fig? Okay, 1 sig fig would become 0.2. Why? Because the 6 is bigger than 5, so that would roll my 1 up. Okay, 2 sig fig then is 0.17. 3 sig fig, I'd be writing down those three numbers. The number after is bigger than 5, so that would roll up, so 0.17, and again 0.1667 for 4 sig fig. Okay, so rearranging equations then, let's have a quick look at this. So when you rearrange an equation, you've got to draw your own equation triangle, and in that equation triangle we already have our times by and our divide by signs there. Now then, you've got to use the sign that's already in the equation to work out where to put them. So in this case we've got a times, so we're going to put our F and our lambda on either side of the multiply, meaning our V has to go up at the top. Now, just like we can see in these ones over here, these have got already filled in. So how do we use these equation triangles once we've filled them in? Well, what we're going to do is we're going to cover up the thing you're looking for, and you're going to do what's left. So if on this example here you want to find V, you would cover up V so you can't see it anymore, and you do what's left from left to right or top to bottom. So F times lambda. Over here, if you want to find F, you cover up F, you do V divided by lambda. If you want to find lambda, you do V divided by F. Okay, so let's have a quick look here at how to rearrange an equation that has more than 3 terms in it. So let's just say they told you to look on the physics equation sheet, and you identified that you've got to use V squared minus U squared equals 2AS. So let's just say, for argument's sake, you're given U, A, and S. Now in this equation, U means initial speed of something, A means the acceleration it's feeling, it's doing, and then S meaning the distance from the start. So given these values here then, and let's just say I'm being asked to find V on its own. So I want to find the final speed that this object is going to reach. Okay, so these are the steps you need to go through. You always want to write down the equation. You've got to substitute your numbers into the right places. You've got to do the sums you can, and then to get the term you need on its own, you've got to do whatever the opposite is to both sides. And I'll show you what I mean. Okay, so always write down the equation. Put your numbers then in the right places, bearing in mind if you've got a squared or a 2 there, that still needs to appear. So here we go, V squared minus 5 squared, my U is 5, equals 2, because that's in the equation there, times 15, because A is 15, and S times 20, it says down here. So do the sums you can. So write it out again, but this time we can do our 5 squared, and we can do this sum over here, just to simplify it a little bit. So we've got V squared minus 25 equals 600. Now we want V on its own, so we've got to get rid of the minus 25 first. So get rid of the minus 25, 600 plus 25 equals V squared. Then, once we've added those two together, and it's 625, we've got to take the square root of both sides. So we've got v squared equals that. We've got to do v equals the square root of 625. And we find that the square root of 625 is 25 meters per second. Okay, so these are the steps you want to follow. Write down the equation, put your numbers in the right places, do the sums you can, do the opposite of any signs to get rid of them so you can get the thing you're looking for on its own. Okay, those are the math skills and the required practicals. Now we're going to spend a few minutes just going through some of the top tips that I think will help you with forces, waves, electromagnetism, and for those separate scientists, the space topic at the end. Okay, so forces. Forces, if they're balanced forces, if they're the same size forces and they're in opposite directions, this is going to mean that an object is constant speed or stationary. Stationary meaning stopped. If they've got unbalanced forces, meaning one is bigger on one side than the other, it's going to be accelerating or decelerating, speeding up or slowing down. And this resultant force, if you've got multiple forces acting on an object, and resultant force just means overall force. So this one's got equal forces on both sides. It's going to have a resultant force of 0, meaning that it is stationary or constant speed. This one again is already moving in a direction, so we know it can't be stationary. And look out for that in questions, because they love telling you an airplane is moving down a runway under balanced forces. What is its motion? So you've got to say it's constant speed. Or it could be with unbalanced forces. So maybe it's accelerating because it's got a bigger forward force than backward force. Okay, so this resultant force is just the, if they're both in the same direction, you'll add them together. If they're in opposite directions, you'll find the difference of them. Okay, so if we have someone pushing a vehicle or making something move because they're applying a force, we're going to be using F equals ma, force equals mass times acceleration. And acceleration means change in speed per second. It's how quickly the speed is changing each second. So using acceleration equals final speed, take away start speed, divided by the time taken. Now, with forces, we get they may ask about scalar quantities or vector quantities in this. So, for example, time is a scalar quantities. It has no direction, it only has size. Whereas acceleration or a force would be a vector quantity because it has both size and direction. Okay, so distance time graphs then. So with a distance time graph, the gradient tells us the speed. So if I was to draw a line coming along here and being like that, we can compare here what the motion is doing. So for this part here, we have got a constant speed, stopped, and a faster speed here. And that's because the gradient tells us the speed. So the steeper the line, the faster. A horizontal line means stopped or stationary. If we've got a line which starts to curve upwards, that there will be accelerating. And if we get a curve which is already going up but now starting to curve to the flat, that's going to be decelerating. I appear not to be able to write properly, but decelerating and accelerating. Okay, now if you need to take the gradient of a line, if I just get rid of all this that I've got here and I make a line going, let's say, all the way over there. Now, you could, to work out the gradient, we need to do the change in y over the change in x, the change in these values here divided by the change in those values there. And it's not just a case of counting the squares. We need to be counting the squares and working out what one square equals. So let's just have a look at this example here. Now, the easiest place for me to draw a triangle would be from here to here, because the line goes through the corner of squares, so it's a little bit easier for me to work out. But let's just say I had something that went, for example, a little bit like that was my line. So in this example, I'm going to want to be able to take my line from where it goes through a corner. So I want maybe my triangle to look like that. Okay, I can count up the squares, which is 15 squares, or 3 big squares, and 3 big squares also happens to be 3 meters. So my change in distance is 3 meters. My change in time there is 2 meters. So I'm using the scale along the bottom to tell me that. Okay, so for this, it would be 3 divided by 2 would tell me my my speed. Okay, velocity time graph then. So the velocity time graph on our key facts here, the gradient in this case, the steepness of the line tells us the acceleration. So if we have a look at maybe a section of a graph that comes like that, another flat line, and now we've got a slightly steeper line. So this is going to be a change in speed. We can see it's changing speed because the numbers up the side are changing. The speed is changing each second. So we're increasing in speed, we're accelerating. This bit here, we're at a constant speed now. The speed doesn't change between 3 and 5 seconds. And this bit here, we're really steep, so we've got a high acceleration. So the speed is increasing more quickly during this between 5 and 6 seconds. Now, a flat line means constant speed here. Now then, the area under a line tells us the distance travelled. Okay, so let's just say a question asks you to work out the distance travelled in the first 3 seconds. How would you work out the area of that? Well, just like in maths, we would do half times base times height. Okay, so we would do 0.5 times the base times by the height would give us an answer of 3 meters had been covered in that time. Okay, so area between the line and the bottom and the x-axis there tells you the distance that is travelled by that object. Okay, so forces then continued. Mass is how much stuff you're made of. It's measured in kilograms. Weight is how hard your mass pushes on the ground, measured in newtons. Okay, so weight equals mass times gravity, where weight is measured in newtons, mass is measured in kilograms, gravity newtons per kilo. Okay, so terminal velocity then, when things are falling and we've got our weight pulling us down and the force of gravity pulling us down, terminal velocity, that maximum speed you can reach, depends on 2 things, your shape and your area. Terminal velocity is a constant speed, so the forces are balanced. Now, air resistance force then upwards will be the same size as the gravity force downwards. Now, why is it then that falling things reach a top speed as they fall through the air? Okay, so they love asking questions like this. So as the object falls, it gets faster. When you first step out of an aeroplane, you're not moving at all. And then as time goes by, you're accelerating, so your speed gets faster. Air resistance increases with speed. So as you fall faster, you're pushing more air out of the way each second, so the air resistance is more. The air resistance increases with speed until it is as large as the downward force from the weight. When they balance, the object no longer accelerates. The resultant force becomes 0. When the resultant force is 0, it's not speeding up or slowing down. It's at its maximum terminal velocity. Okay, waves then. So 2 different types of waves. We've got our transverse wave. We've got our longitudinal wave shown on a slinky here. Transverse waves, we've got the vibrations are at 90 degrees to the direction of energy transfer. The hand is moving up and down. The wave is moving left to right. So the vibrations are at 90 degrees to the direction of travel. In this one, the hand is moving in the same direction as the slinky. So we get areas where they're really bunched up. That's called a compression. Get areas where they're more spread out. That's a rare refraction or expansion. And we can say that longitudinal waves, the vibrations are parallel to the direction of energy transfer. So for example, sound is a longitudinal wave, light is a transverse wave, along with all the other electromagnetic waves. So for a transverse wave, we need to be able to label the different parts on it. We've got our peaks at the top, we've got our troughs at the bottom. Now we've got a wavelength, and a wavelength can be shown from peak to peak. It can be shown from trough to trough. Okay, or it can be shown from center point to center point. They are all exactly the same length, just making sure it includes an up and a down bit for one wavelength. Okay, the other part on here is we have to know the amplitude. So the amplitude goes from the midpoint to the top, or the amplitude goes from the midpoint to the bottom. Now they love asking about that. Why? Because the most common mistake for that is to say that the amplitude is the height of the wave. The amplitude is not the height of the wave. No. It's just half the height of the wave. Okay, so on our longitudinal wave, like an air wave, we might be able to see these patches where the particles are more compressed and see the areas where they're slightly further apart. We're going to see that a wavelength there is from compression to compression. It could be from the start of the compression to the start of the next compression. It could be at the end of a compression to the end of the next compression. It could be from the middle of a rarefaction to the middle of a rarefaction. Each of those lines is the same length. It's just got to be from the same repeating part of the unit to the next, including a rarefaction and a compression. And they seem to like asking questions about that too. Okay, so frequency of a wave, we've come across this already. That means how many waves per second go past. A time period is how long one wave takes to go past, and they're related with that equation I showed us earlier of t equals 1 over f. Okay, so electromagnetic waves then, knowing the order of these is really important, but also knowing that they can go forwards or backwards in the order. So going from longest to shortest then, we've got radio, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays, or what you may be more familiar with is going from shorter to longer, gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. And you do need to know that radio waves have got the longest waves, gamma rays have got the shortest waves. And if we think about it, that helps us to understand why these ones are dangerous. These ones are dangerous because they've got short wavelengths, they can penetrate inside our body easily. These ones, much longer wavelengths, have less effect because they can't penetrate our body so easily. Other things you need to know, frequency, these ones, not only do they have a really short wavelength, but in order to still travel at the speed of light, v equals f times lambda, if I make the frequency really high, I have to make the wavelength really short to still travel at the speed of light. So where the wavelength is really short, the frequency is really high, and the same the other way around. When the wavelength becomes high, the frequency becomes low. For the speed of all of these things to still be the same as each other. So every one of these things on this page all travels at the speed of light, all goes at 3 times 10 to the 8 meters per second. So magnetism then, the Earth acts like a magnet because it's got a liquid core of iron and nickel that acts like a magnet, and we can see the magnetic field lines around the Earth by using a compass, or we can plot the magnetic field lines around a bar magnet, and they both act in the same way. So what do these lines show us then? Well, the field lines show the force of attraction felt by another North Pole. The closer the lines are, the stronger the force. So that's why around the poles is where the force is strongest. And the field lines, you'll notice, go from north to south. Okay, so when we bring two poles together, opposite poles, north and north, they attract each other. They'll both feel a force of attraction there. Bringing the same poles together, they feel a force of repulsion. And you've got to use these keywords, attract and repel. Now, if we want to find these field lines for ourselves, we can place little mini compasses around a bar magnet, and they'll all point in the direction of the field lines. So we can join those up, mark on with an N the North Pole, and we can draw the lines with an arrow going from north to south. Okay, so a little bit more on electromagnetism then. When you get current going through a wire, it creates a magnetic field around it. So a moving charge, like electrons in electricity, they create a magnetic field. Now, if we get this piece of wire here and we curl it up and we put current through it, we get a much stronger magnetic field. And it's very similar to the magnetic field inside a magnet, except this time we've got the lines going through the middle of it. These lines here should be straight lines because we've got a strong uniform field inside that electromagnet. So describing it as a strong uniform field is may be important. Okay, so if we wanted to increase the length of the strength, of a solenoid is just a coil of wire. If we put a soft iron core inside it, put a piece of metal or an iron nail there, that makes the electromagnet stronger. We can increase the current. Okay, so putting more current through it increases the strength of the magnetic field. We can increase the number of turns on the coil. So the more turns there are, the stronger it is as well. Now, why is this really useful? We can turn electromagnets on and off. We can increase the strength of a magnet by having more coils or more current. And that's a really important property. And it can help us in maybe moving scrap metal around a scrapyard. And if we want to find the direction, of the field lines, we can find this from the right-hand grip rule. So just like we can see here, the fingers can coil around a wire with my thumb pointing in the direction of the current, and it will tell me the direction of the field lines. You can see those little arrows there. My fingers curl around the wire, showing me the directions of the field lines. Or with a solenoid or electromagnet, if I curl my fingers around in the direction of the current going through the coils there, my thumb will point in the direction of the north of the magnet. Okay, now the rest of this broadcast is now for higher tier or separate science only. So thank you very much, all the combined scientists, for listening to this. Really good luck for tomorrow's exam. It's the last of your science exams, and for many of you, it's the last of all of your exams. So work hard tonight, make sure you're ready for it. Best of luck, and I'm looking forward to hearing how the paper's gone. Okay, so for higher tier then, just a little bit on the Fleming's left-hand rule and making a wire move near magnets. So a current-carrying wire, a wire with current through it, is placed in a magnetic field, it will experience a force. Why? Because the magnetic field around the wire, caused by the moving charges in the current, will interact with the magnetic field from the magnet. You're basically bringing two magnets close to each other. Now, we can use Fleming's left-hand rule to help us to work out the direction that this wire, this current-carrying wire that's in a magnetic field, to find out which way it'll move. So to use Fleming's left-hand rule, you need to know current always flows plus to minus. So in this diagram, current is moving away from us. So you need to get your middle finger, your swearing finger, and point it into the screen. Okay, now your field lines, magnetic field lines, always go north to south. So you're going to flick your first finger, your pointing finger, and that's going to go to that side. So your middle finger should be pointed into the screen. Your first pointy finger should be pointing to the right, meaning your thumb now should be already pointing down. And the thumb tells us the direction of the force or the direction of the movement. Okay? So just pause that and have another go at it, rewind it if you want to, and have another go at that. So this could be where the equation fits in of making a wire feel a force. How strong is that force it feels? Well, it's the magnetic flux density, the strength of the magnets, times by the current going in the wire, times by how long the wire is that's cutting through the lines. Okay, now the rest of this broadcast is now for separate science only. If you've been higher tier and you've been listening in, thank you very much. Best of luck with your exam tomorrow, and looking forward to seeing how it goes. Okay, separate scientists then, let's whiz through just the space topic. I would like to say for any separate scientists that there is an extra hour video for all of the separate science that are recorded at the weekends. That goes into a little bit more detail of all the separate science bits for topics 5, 6 and 7 as well. But this is just to whiz through a few things to make sure you're happy with them with the space topic 8 only. Okay, so within our solar system, there's one star. We've got the Sun plus 8 planets and the dwarf planets. There's a few dwarf planets that orbit around the Sun. Now, even the moons that orbit planets, they're called natural satellites. They're also part of our solar system. And our solar system is part of the Milky Way galaxy. And our Sun was formed from a cloud of dust and gas, a nebula pulled together by gravitational attraction. So let's fly through the life cycle of a star here. So we've got light stars are going to be in yellow. They're up to 8 times the mass of our Sun. Medium stars in orange, and massive stars are in red here. So gas and dust will be drawn together due to gravity. They will fall inwards. Friction will make them get hot. And as they fall inwards and they get hot, they'll start to do nuclear fusion. When they do nuclear fusion, the star will light up, and it stops being a protostar, proto meaning like prototype, new, protostar, and it turns into a main sequence star when fusion starts. Now, during fusion, it's going to be converting hydrogen into helium, light nuclei into heavier nuclei. Now, our Sun is going to follow the path of a small mass star. So it's going to, once it's used up all of its fuel here, it's going to turn into a red giant. It's going to expand. And then once it's expanded and it's used up the rest of its fuel, it's going to cool and it's going to go down into a white dwarf. And then eventually, once it's used up all of its fuel in nuclear fusion, it's going to turn into a black dwarf, and we won't be able to see it anymore because it doesn't give out light. Now, for heavier stars, anything heavier than 8 times the mass of our Sun, heavier mass stars will turn into a red supergiant. Now, the red supergiant will expand very large and will keep using up its fuels inside there, producing all of the elements all the way up to iron. Now, once it's used all of its fuel up to iron in the process of fusion, it's going to collapse in on itself really rapidly. And when it collapses in on itself, it causes a huge explosion. The largest explosions in the universe are supernova, at the death of a star. Now, during the supernova explosion, all of the elements bigger, heavier than iron are made, and they will be scattered out into the universe, into the galaxy. Now, left behind a supernova, you've got a small neutron star, very small object, which is very dense. And the very heaviest objects, the heaviest of them all, will end up collapsing as a neutron star and turning into a black hole. Of course, you can't see it because no light can escape from it. Okay, orbital motion then. So things going around in circles like planets orbiting a star. So velocity is speed and direction. Now, when something is in circular motion, the speed is constantly changing, as we can see here. There may be the direction at any one particular moment is at 90 degrees to the radius, but the direction is constantly changing, so we can say the velocity is changing. And if the velocity is changing, then we say it's accelerating. Okay, so if a planet or moon is in a stable orbit, if it's in a stable orbit, if the speed changes, the orbit radius has to change too. So if things are going to be moving faster, they have to be at a smaller radius to stay in a stable orbit. If they're going to be slowing down, they have to go in a larger radius to keep the orbit stable. And this is because the force of, I need to stop doing that. This is because the force of gravity is stronger the closer to the object you are. The closer to the sun you are, the stronger the gravity. That's why Mercury travels fastest. It's got a stronger force pulling it into the center of the circle, so it travels the fastest. Okay, so redshift. I really like this redshift topic because it proves to us what our universe is doing. Okay, if an object, let's pick on a galaxy here, and we've got two observers. If this galaxy is moving towards an observer, the galaxy is going to be giving out a light wave, and every second that galaxy is going to be moving towards the observer. Now, the effect that has of giving out a wave each second, let's say giving out a wave peak here each second, if you move towards those wave peaks, as you give them out, you're going to be bunching them up. You're going to be closer to the next one. So the effect is that it shortens the wavelength of the wave being given out. Now, if the galaxy is moving away from an observer, it has the opposite effect. As the object moves away, the wavelength gets longer. Now, this is called the Doppler effect, and we can hear it really nicely with a racing car going past you at a racing track, or a fire engine coming towards you down the road and then going past you. You hear, as the object gets closer to you, the pitch, the frequency gets higher, and as it goes past you, the pitch and the frequency get lower again. Okay, so what's this got to do with the evidence of our universe expanding? Okay, this color chart here is called a spectrum, and it shows us the rainbow of light that comes from our nearest star, the sun. And you can see here that there are lines which are black. These are called absorption lines. An absorption line is where the elements of the star itself have absorbed those particular frequencies. Okay, so hydrogen and helium in our star would be absorbing, let's say, these absorption lines here. Okay, so with this should be the same absorption line, whether it comes from our star or a different star. I'm just trying to break the hangout here. Let's try and stop that. Okay, so this is our absorption lines. Now, when an object is moving away from us, these absorption lines move to one side. So you can see here that on this chart here, the absorption lines have moved towards the red end, just ever so slightly have been shifted over. And this is because of this Doppler effect, that because the galaxy is moving away from us, that the lines, the wave has been stretched, so those same absorption lines are still there, but they've been shifted towards the red end, as in the light has become stretched. Now, for any object moving towards us, the absorption lines move to the shorter end, to the blue end, so we say it's blue shifted. Now, let's see how we might write that out. So how is this evidence for the universe expanding? How does it prove it? Okay, well, light from distant galaxies is more red than expected. The absorption lines in the light are shifted to the red end of the spectrum. The further the galaxy, the more red shifted it is, so the faster it's moving. So when we look up at the sky at night, the more distant the light is, the redder it is. And this tells us that those are moving faster away from us than the things which are close to us. Now, the only way to explain this is that all of space itself is expanding, the very space between galaxies is getting larger. If we rewind the position of all these galaxies, they all start off in one place. Okay, it's, I think about 13 to 14 billion years ago, all of the galaxies started off together, and that proves the Big Bang theory as well, that all of the universe started in an instant at the same time. Ladies and gentlemen, best of luck and best wishes for your exams tomorrow. I really hope they go well. Get some rest. Watch the other separate science video if you want to. I'm not going to play any music tonight in case it gets copyrighted. So thank you very much and good night.